Welcome to lecture 8 of MCS 472, Industrial Math and Computation. So this is the third lecture of the third week where we introduce filtering, signals and filters. At the end of this third week, we will end up with feedback. There will be more feedback in a later part of the course. But mainly today we are introducing Bode plots. Last time we proved two theorems on filtering. The second theorem will be repeated and will actually be used to interpret the effect of a filter. Next week we will be designing filters using Fourier transforms, the discrete Fourier transform and the fast Fourier transform. This lecture is also used to introduce more terminology. We will encounter another unit, decibels, which is commonly used to describe power ratios. Okay, but let's start with Bode plots. This lecture is introducing, so in this week we introduced a lot of new terminology, and this lecture will attempt as much as possible to be self-contained. So let's start with an averaging filter. So what does an averaging filter do? It takes on input a sequence of numbers, and then it adds up two consecutive numbers and averages them. So the recipe is quite simple. So we have seen as our first theorem in the previous lecture that if we know the response of the unit impulse, so here you see what the signal does to the signal 1 0 0 0 0, that's the unit impulse, that the impulse response determines a linear time invariant and causal filter. So I'm using this type of filter also to introduce what is called the finite impulse response filter. So we see that the impulse response is finite, so only finitely many different non-zero numbers, so you can truncate it here essentially after the first two numbers. So this is called then a finite impulse response filter. Fine, easy to define. What good does it do? Well, that's the main question that we will try to answer, for which we try to motivate the notion of Bode plots. So, but let's first recall the transfer function. So what is the transfer function again? So we can read off the transfer function from the impulse response. 1/2, 1/2 will be the first two coefficients in the Laurent series of the transfer function. But we can also compute it from the transfer function, from the Z transform of the input. So this slide accomplishes hopefully many the recalling of many concepts that we have introduced in earlier lectures. So you see here the Z transform of the input. So it is the Laurent series of all the input numbers. What good does a Z transform do for us? Well, it allows us to represent the input signal in a very compact manner when we have an explicit form of the Laurent series, and often we do. So the delay, so the averaging filter can be expressed as the sum of the input signal and the delayed signal, the unit delay, for which we derived earlier that the Z transform of the unit delay is the Z transform divided by the symbol Z. So the averaging then happens by the division, and you see the transfer function has as coefficients 1/2, 1/2. So these are the coefficients of the impulse response. Very good. We have a mathematical framework. We have some tools, the Laurent series in particular, to express signals, so via the Z transform, and also we can say what it is that actually a filter does via this transfer function. Okay, but what does this now mean if you, so we know what a unit delay is, but what does an averaging filter do to some signals, to a signal? Okay, to that end, we recall a theorem we proved last time. So this theorem was used to introduce the notion of a signal as a sine function. So our filters, they will be linear, time invariant, and causal. So for such filters, the output is again a sine function, but it has a change in amplitude. We call that the amplitude gain, and there is also a phase shift. And as the transfer function is defining the filter, we can read off the gain from the transfer function, and also the phase shift can be gotten from the transfer function. Where we keep in mind that we have the unit signal given continuously as a signal. So for Fourier transforms will actually show that every signal is a composition of sine functions. So you may wonder, why do we actually work with a sine function? What's the point of all this? But sine functions are our building blocks. They are running at some frequency, and we expressed this in hertz, so the number of cycles per second. And we work with numbers on input, so we have a sampling rate. So every capital T seconds, we have a number, a value that comes in when we evaluate that sine function. Complex numbers are important. So in mathematics, we imagine things. So we call the imaginary unit a unit, but actually they are very much real here, and to compute with signals, very much essential. We proved this theorem, so the mathematics all worked out fine. Great. But what does it actually mean now? Okay, so let us compute this for the averaging filter, because we want to know what does an averaging filter do to an input signal. Okay, so we're going to compute the amplitude gain. That's the radius of the transfer function evaluated at this e to the power I omega t. So omega incorporates the frequency. And also the sampling rate is also in there. So let's evaluate this. So we evaluate the transfer function at this e to the power I omega t. So we use the formulas that we know from the polar representation of complex numbers. So they're actually mentioned here. So for any complex number, the magnitude is the square root of the sum of the squares of the real and the imaginary parts. And the angle or the argument we get from the inverse tangent of the imaginary part over the real part. So here they are, our two quantities, that the amplitude gain, so it's a positive number, and our phase shift. So this is the theorem, an example of the theorem. So actually any good theorem should actually start with an example why you would need the theorem, and then you would have the proof. But we did it backwards. So we first gave the proof, which also allowed us. The proof is very constructive in the sense that it showed us the complex numbers, how they came in and were related with the science. So in a way, it was not that pedagogically unjustified. So we have these two expressions now at the bottom of the slide. We can stare at them a little bit, but they actually haven't really, unless we know already what it is, but it's actually not really that revealing yet what the averaging filter does. Okay, let's do plotting. Okay. So I'm trying to explain here what these formulas still mean. So we have the radius expressed as a function of the omega and the sampling rate t. So the omega incorporates the frequency of the input signal. The sampling rate is the rate at which we have sampled the signal. So there are two variables in this expression. So we will fix the sampling rate. Very natural in our setting. So we deal with sequences of numbers on input. And we will see what these expressions look like if the frequencies range from 0 to the sampling rate. Okay, here is another thing that we may wonder about our filter. Is our filter stable? And I think it may not be that. So what is a stable filter? It follows from the definition. If we have a bounded input, the filter will also produce a bounded output. So the averaging filter is stable. So before we actually get to the plotting, here is an exercise where we consider the transfer function of a filter. The numerator is a linear expression and the denominator has two roots. Let's consider them distinct. Now show that the filter is stable if and only if the roots of the denominator are strictly less than 1. So the setup of this question, especially the alpha 1 different from alpha 2, is set up in the context of the partial fraction decomposition. So construct the partial fraction decomposition for this transfer function, which we considered in lecture 6. So the partial fraction decomposition will write the transfer function as the sum of two much more, it will separate out the two roots of the denominator. So you will have two fractions, but instead of having a quadratic denominator, you will have a linear denominator. And that will allow you to write down what the signals are. So from the transfer function, the roots of the denominator, you can get the actual numbers. And you will see that the roots play an important role in the geometric progression of the numbers. So the sum of two the sum of two bounded inputs is again bounded. The same with the sum of two bounded outputs is again bounded. So you will use that property as well. So by this I have kind of solved the exercise in words. What you need to do to actually solve the exercise is to apply the partial fraction decomposition and exploit the fact that our filters are linear. Okay, the averaging filter is stable. Now we will make polar plots. So here, with our polar coordinates again, we were thinking in polar coordinates already last lecture. So back then on the board, I sketched a very rudimentary plot of the polar representation of a complex number. In polar coordinates, also real objects. So circle has a very simple representation. So here it is, and that is also what you use to make polar plots in Julia. So there is a JupyTer notebook that corresponds to this lecture that is available on this website, on the course website. I will later also list the instructions to make plots very quickly in Julia. So here is then the polar plot of the averaging filter. So we let again an angle go. So now actually the important parameter here, the independent parameter, are the frequency. So we have the frequency n that goes from 0 to 1000. So the capital T is 1 over 1000. So the omega is 2 times pi times n, where n ranges from 0 to 1000. So we make this plot. So we have an angle that varies, the phi, and we have a radius, corresponding radius. So the polar plot is represented here. It's another circle. So in a way, what good is that? Now we see another circle, but note that the circle goes to the origin. Okay, and so we have an amplitude. So on the circle, the amplitude is going to range between 0 going to 1 and then it's going to 0 again. So depending on the n. Yeah, so the circle is actually, if I would stop here with the plotting, it would kind of anticlimactic, because I mean, how is that now revealing? But let me show you the Bode plot. So Bode is named after a person, and in our department you may also know somebody with that last name. The pronunciation Bode is because the name after which the plot is named is an American. So I pronounce Bode the American way, not the German way. So here are the complete instructions to make the polar plot in Julia. Except that I may have skipped the critical projection equals colon polar. I'm sorry, I had to cut something, and perhaps the critical thing went out. But in any case, so if you make plots, it's important here too that we are sampling. So we are sampling dots. So you can see the frequency, the frequency range from 0 to 1000 in steps of 1. The 1 might not have been necessary, but just for the sake of clarity. So then the omega has as the independent variable here are the frequency. So what actually we want to see is what is the amplitude gain and the phase shift whenever the independent variable is changing. Okay, so making plots next to each other is also quite straightforward. So here you see the making of the plot straightforward next to each other. And here is then the main result of the Bode plot. So I'm in the middle of this lecture now, also kind of the central concept explained. So we see two plots. At the left, we see the evolution of the gain. So for the independent parameter, so the frequency n that ranged between 0 and 1000, so that's the gain. We see we were on the circle I indicated, but I've seen the Bode plots first before I could say something about the circle. Here it's much more obvious. So you see the gain, or perhaps more the loss of the amplitude, goes from 1 to 0 and then 0 to 1 again. So there is also this phase shift that follows this pattern. So we have signals that are coming in at frequencies. So if you have a frequency, say, that comes in at 10, then the amplitude of the output signal will be a little bit less than the input signal, will be less than 1. So we say that the higher frequencies are attenuated, another terminology. So one says that the filter has a low pass characteristic. So that's what the plot shows. So, and in a way, with hindsight, what is it that this filter does? It averages. It averages the input signal. So, I mean, that actually means that it will have some smoothing effect, if you like. Okay, so it's a filter in the sense that if you're running at 500 hertz here, your signal will be actually knocked out. So you will have no signal anymore. And the 500 is actually half the 1000. So that is a property of the sampling rate. So the shape of this Bode plot, so the textbooks plots it first at 0 to 5000, but here we plotted between 0 and 1000. You see this repetitive effect, but that's an artifact of the sampling rate. And that's also something that one needs to be concerned with when one does the digital filtering. That and we had this in the previous exercises as well. So let me go immediately to the exercise. So in the previous exercise on the board in class, I solved this exercise, and I can say now to you as the listener who is deprived of this board, that the board is here behind me. I could actually write it down. So it is 1, so the transfer function. So let me write it down. So using the board, so the transfer function is 1 plus z minus 6. And yes, so I should have used black, but I hope it um, is still visible. So y minus 6, well, the sine function has a natural symmetry that can be exploited. We sample here at 12 times the frequency of the signal. So the 6 is the 6 delay. So we have the U1 that gets knocked out by the U6. So the Bode plot should reveal this. So if you make the Bode plot, you should see the effect of this filter. But if you make this Bode plot, so you make this Bode plot for 7 at a sampling rate of 720, and you will actually see which signals. So this will also be the signal that's running at 120 hertz you will lose. But note that the purpose of this filter was to knock out a signal that's running at high frequency, and that is noise. So as an artifact, you will, as a side effect, not an artifact, as a side effect, you will knock out also other signals. So that, by the way, was also asked in the previous lecture in the exercise 3. So these exercises are kind of linked. So the Bode plot also actually answers that second part of that third exercise, which you may have guessed, or which you may have, which was able to solve numerically if you looked at the numbers. Okay, so we are halfway. So we have essentially the first part of this lecture is done. Let me emphasize the aliasing effect of a filter. So we can also get this from the periodic nature of the outcome of the theorem. So if in the theorem we take the transfer function and we evaluate that transfer function and we get a complex number. But you see that a complex number can be the same if we have a signal where we add simply 2 pi to it, a multiple of 2 pi even. So remember the exercises in the first batch. No, I'm sorry, forget this remark now. So the point here is that the response depends only on this modulo 2 pi. So if you have seen Western movies, then you may have seen the effect that certain wagon wheels were rotating too slowly or even in the opposite direction of the motion. And that's because in a digital filter you can actually not distinguish between the sample signal of the frequencies that are related to the sampling frequency. So there is a technical term, congruent modulo the sampling frequency. So this is a defect, and one often oversamples, and sometimes in the analog to digital converters the hardware may actually even already have something built into this to make sure that you do not lose certain critical signals. Okay, experiment with this. So we had the 500 hertz signal that the averaging filter knocked out. And that 500 was most likely an artifact of the sampling rate, which was 1000. Look at the Bode plot, also make another Bode plot now, but simply change the parameter t to 1000 to 2000, so from 1000 to 2000, and compare the Bode plots now. So I predict here that the 500 hertz signal was removed because of our sampling rate. and had actually was not so characteristic to the um, averaging filter. So it is not so that every averaging filter will remove 500 hertz signal. Okay, so then one unit that you may have encountered are decibels, so written in plural. So decibels are here defined as the 10 of the power log of a ratio. So why decibels? They are used to comprehend and to express the ratios of vastly different magnitude. Um, Kind of if you have to go from a classical scale uh, to a logarithmic scale. So in some sense, you can interpret our when we go from the time domain to the frequency domain. Also, the decibels will make the computation of gains and losses of cascaded systems. So that's when we put several filters next to each other. Then actually the gains and the losses are then expressed as additions or subtractions in case of loss. Okay, feedback is the last topic I wanted to cover. Actually, the second important topic. We will see more about feedback in the later part of this course um, when we see frequency domain methods. So here it fits quite well when we want to look at the control of a process. So you can already think also about signals. Sometimes you want to amplify a signal, sometimes you want to dampen it. So we have a process schematically presented here, and we use the letter P for process, but also the letter P for its transfer function. Then we have that the transfer function of the output Y can be written as the product of the transfer function of the process times the transfer function of the input. Or more precisely, even the Z transform of the output is the transfer function of the process times the Z transform of the input. So what does feedback do? It takes the output of the process and it feeds it back to the input. So the plus and the minus are indicating the correction. So the correction here in the feedback, we subtract the controller, or also called the compensator, we subtract that from the output. So we have now a closed loop system. That's also what we are looking now. So it could be that the original process is unstable, but with the controller on there, the process itself becomes stable. So the most original examples of the controller were the outlets from the steam engines. So there is a valve there that if the valve remains shut, your steam tank explodes. But as the pressure builds, the valve comes open, and then the process does not run out of control. Once the steam actually, once the pressure drops, the valve closes again. So we can mathematically work with the closed loop system, and now we have another process. The closed loop system corrects the original output, and we have a transfer function of this closed loop system that is defined by the transfer function of the original process, the P, and the transfer function of the compensator. So we have this expression that is the fraction. Okay, so let's look at the numerical example. We can stabilize an unstable plant, or here we have a process that, given a stable input, so it's actually a finite input, the unit impulse, produces an unbounded output. One can see this also directly from the z transform if one looks at the transfer function. So if you read now the formula for the transfer function from right to left, so we have the definition of the z transform of the output, and we can write this as the rational form 1 over 1 minus 2z. The Then further to the left, so if we look at the z over z minus 2, the 2 is the geometric ratio. So again, the motivation why now we actually write the picture of the closed loop system is now replacing the p by its transfer function. So we see the unstable process that doubles the numbers in each step. So it grows exponentially at ratio 2. But we can fix this with a constant compensator with ratio 3 halves. So the h here is represented by that ratio 3 halves. How come? How come this is now a stable plant or a stabilized process? Well, look at the closed loop function. So the transfer function of the closed loop is then as follows. So we compute it with the formula that we derived. So if the arithmetic works out fine, so we multiply p with h. So the h is the constant 3 halves. We simplify, and the ratio 4/5 comes in. So as we have the transfer function of the closed loop system, so this is here central, we can, with the Laurent series expansion, we can see the geometric progression of the series. So the output is now 2/5 multiplied by 1 or a power of 4/5. But the 4/5 goes to 0. So our input will die out, come smaller and smaller as we process, as we progress in time. So the resulting closed loop is now stable, is stabilized by a constant feedback. Okay, so our last exercise, I'm on my last slide, and this lecture was efficient, so in 40 minutes I am done. So we can generalize this. So a constant feedback, beta, is computed from the alpha in the denominator coefficient. So what you should do is you take so the exercise is being solved by computing the transfer function of the closed loop system. And looking at the Laurent series expansion of the transfer function of the closed loop system. Okay, so that is the essence of this lecture. What I intended to do in this lecture is to illustrate the main theorem of filter design that we proved last time. We illustrated this on an averaging filter, and there is a strong relationship between designing of systems, so control of linear of systems theory, and signal processing. So signal processing and systems control, they are very closely related. So I hope that this also somehow is made clear in this lecture. Next week in this course, we will see discrete Fourier transforms and fast Fourier transforms. So that will be the fourth week, which kind of combines essential algorithms. So the Fourier transforms are one of the belong to the top 20 of the algorithms of the past century. They are used both in symbolic computation and in numerical computation. So in a way, this course is talking about the mathematics for industry, but it's also in essence a little bit symbolic computation too, and numerical analysis too. Okay, thank you for watching.